So guys, in this video, one of the most important thing of this chapter we are going to see called as your Ellingham diagram. Of course, in our previous video, we saw that whenever we have to reduce a particular metal oxide to the metal, we need a reducing agent. Since in industries, of course, in each industry we will be having a protocol. That is, a procedure will be given. Similarly, in that of your metallurgical process when you are carrying out, such industries are also well aware that when you are having a particular metal oxide, what particular reducing agent you have to choose. So now in this particular topic, we are going to see that how that particular reducing agent is chosen by this Ellingham diagram. So first and the foremost thing, let us know that what do you mean by this Ellingham diagram? So basically it's a plot, or we can say it's a graph which gives you the curves, the curves which are obtained by plotting the standard free energy, that is your delta G, versus your temperature for the oxidation of various metals and also of course carbon using just 1 mole of oxygen. That is, if I just give you my textbook part, let us see this. So this is the plot called as that of your Ellingham diagram. So what it is saying, they are the curves. So whatever the curves whatever the lines you're seeing, this is called as the curves. Curves means nothing, it's a graph. So the curves which are obtained by plotting standard free energy, you can just see my y-axis, it's in standard free energy, G naught. That is the reason. G naught means what? Anything a naught is coming means it is standard form. G means your free energy. So standard free energy versus your temperature, which is obtained by the oxidation of the metals. You can just see over here, copper to copper oxide. But what is the main criteria? We have used just 1 mole of oxygen in all the cases. So this diagram is called as what? Ellingham diagram. So the curves which are obtained by plotting the standard free energy versus temperature for the oxidation of the metals to the respective oxides using just 1 mole of oxygen is called as an Ellingham diagram. So before going to the depth of this topic, first and the foremost thing, let us know that what all the things the Ellingham diagrams gives us the information. So of course, when you are having a close observation on this diagram, what you could see, certain lines are going in the positive direction. That is, they are having the positive slopes. You can just see they are all moving in the positive direction. That is, they are linearly going upwards. But certain line, for example, your oxidation of a carbon to carbon monoxide, it is going downwards. So first we will be understanding what is happening in these cases. So certain lines which is having you the positive slope is mainly because of the condition that your delta S is becoming what? Negative. That means what? Of course, this is a plot they have obtained. Ellingham, what he did do? He chose each and every metal. He converted their respective oxides using 1 mole of oxygen. He calculated the value of your delta G using your formula of delta H minus T into delta S at different temperatures. And then when he plotted, he got this diagram. Very much important diagram. So when I'm saying that when these lines are moving upward, what we could just notice is that the delta G is becoming more and more positive. That is, see, if I choose here carbon monoxide, we can choose here zinc itself. Sorry, this is for the zinc. So what is happening from minus 600 to it is going near minus 200. Of course, if I'm going to extrapolate it, it will be going to minus 100, 0. So that is what delta G is becoming positive. So according to the reaction, if delta G, when does it become positive? It is only possible when your delta S is becoming what? Yes, negative. Minus into minus will be giving you the plus. So delta G will be resulting in positive. Delta S is becoming negative means what? The randomness is decreasing. That is, whatever the oxides you are getting, they will be not in the gaseous state. They will be in their solid state where the randomness is decreasing. So that is the reason these curves are approaching towards giving you the positive slope. But can you say why the slope of your carbon to carbon monoxide is negative? Of course, what happens over here? In this case, the delta S becomes positive. Can you say me how? Of course, when I am taking a C plus O2 gives you the CO. We know that whatever the coke we are taking, that will be in the solid state. But whatever the carbon monoxide we are getting, that will be in the gaseous state. So gaseous state means maximum randomness, alva. So maximum randomness iddaga enagutte, delta S will be positive. So when is your delta S positive, what happens? Delta G will result in negative. That is the reason as the randomness increases, the delta G values is going on in the negative direction. That is the reason it is having that of your negative slope. Of course, one more important thing I want to just say it over here. They are not mentioned in this diagram. Important characteristic which has been included in your notes also, which says that, for example, I think this is the curve for that of your silver oxide. That is what Ag plus O2 give rise to AgO. If I put here as 2Ag, yes, alva. So whenever you can just see this curve, that it is the curve of this is going in the positive. It has gone in a minimum temperature itself. It has gone in the positive delta G. So for such reduction of such metals, for example, if I have given with AgO and I have been said that I have to reduce it to Ag, remember for such metals there is no need of any reducing agent. Why? Because by applying whatever the temperature it is required and making it as a delta G positive, I will be getting my silver back. And that is given by the point in your notes as what they are given. There is a point in a curve below which your delta G is negative. That is after this point they have mentioned. Okay. Therefore, MXO is stable, above which MXO will decompose on its own. So that is what they are saying. This, if I take as MXO, this MXO, whatever we are seeing, will be stable only when your delta G are negative. Once this MXO becomes delta G positive, they will remain as unstable. Of course, we know that whenever a compound is unstable, it will try to attain the stability. So it will decompose on its own to give you the respective metal. So importantly, we have seen the three important characteristics, that in the Ellingham diagram, the slope is giving you the positive because there is a decrease in that of your entropy. There is a negative slope because there is an increase in the entropy. Your MXO will be stable only when that of your delta G value is negative. Once a delta G is positive, for such metal oxides there is no need of your reducing agent, because when delta G is positive, respective metal oxide become unstable. In order to become stable, they will decompose by its own and that particular temperature and give you the metal back. Example, I can give one more. That is one more we are having as HgO, mercuric oxide. HgO and AgO nearly in the range of 480 degrees Celsius. Okay, nearly in the range of 480 degrees Celsius, they will decompose on its own to give respective metals Ag and Hg. Okay, because after that 400 degrees Celsius, their delta G is resulting in positive and they are becoming unstable, and that is the reason they will decompose by its own without using any reducing agent. They will be giving you the respective metals. But the most important part I have to discuss over here is how to choose your reducing agent for a particular metal oxide. That is, the fourth important characteristics which is stating by your Ellingham diagram is that if delta G naught versus temperature curve for a metal oxide lies below, okay, lies below, such metal can be used as a metal reducing agent. Such metal can be used to reduce the metal oxide placed above in the Ellingham diagram. That what does it mean is, for example, if I am having this Al2O3, can just notify over here. What I have given is Here. Here you could just notify that I am having now Al2O3 as my metal oxide. Can I use my magnesium oxide as a reducing agent? Of course I can use it. When I can use it? Only when the curve of this metal oxide, the curve what you are choosing as a reducing agent, such reducing agent's metal oxide should lie below the curve of a metal which we are going to reduce. For example, I am having Al2O3. Of course, I can use the magnesium over here as my reducing agent. So what happens over here? I will be getting my aluminium plus I will be getting my magnesium oxide. Not an issue here. 2Al, 3MgO. Yes, 3Mg. But this is only possible when the respective metal oxides, whatever the reducing agent you are choosing, that should be below that of the metal what we have chosen as a metal oxide. Able to understand? That is only possible when the temperature is less than 1473 Kelvin. The same thing they have been said over here. If delta G naught versus temperature curve for a metal oxide lies below, such metal can be used to reduce the metal oxide placed above in the Ellingham diagram. So here now I can reduce Al to O3 to Al by using my magnesium only below the temperature of that of your 1473, because whatever the reducing agent I am choosing, the respective metal oxide curve is lying below. Such metal can be used to reduce the metal oxide which is placed above it. Able to understand? So below 1473, the reducing agent metal oxide is lying below a curve of the metal oxide which I have been given to be reduced. But above 1473, what happens? You can just see that the curves has been switched over. So above 473, what happens is, if I am having magnesium oxide, so this was when it is less than 1473 Kelvin. So above 473, what happens? 1473, I can choose my aluminium as a reducing agent. So why? Because now whatever the reducing agent I have chosen, that will be lower in the curve. So thus curve can be able to reduce the metal oxide which is placed above it. That is what the Ellingham diagram is saying. So now what happens at about 1473, we will be getting our magnesium plus that of your Al2O3. Yes. So here 3Mg, yeah, to Al2O3. So this is the major thing what they are saying with respect to the important thing of your Ellingham diagram. So the fourth characteristic says that which reducing agent we have to choose for a particular metal oxide. Just in your mind, you have to just make sure that whatever the reducing agent you are choosing, okay, such reducing agent's metal oxide curve should lie below a curve for the metal oxide which has been given to you. That is, if you have been given with the aluminium oxide as your ores oxide and you have to reduce it, you can reduce it by seeing the curve which is below it. Such metals can be used. So such metals can be only used when, for example, if you are choosing magnesium, it is lying below that of your curve's metal oxide below 1473. But above 1473, what happens? The reducing agent's metal oxide curve goes upwards, whereas your ores oxide goes downwards. So in this case, you cannot use it. Able to understand? Let us take one more example. You have been given with a metal oxide ore. So this is your ore. So which reagents, which reducing agents you can use? Of course, the reducing agents you can use are carbon monoxide you can use, because you have to see which curve is lying below it. So carbon monoxide you can use, coke you can use, yes, zinc you can use, any of this you can use. but which I am going to choose is it should be economical for me. I should use just minimum temperature. The reaction should take place spontaneously. So for iron to iron oxide, the best reducing agent will be my coke. Able to understand, guys? Very much important, which will be seen. The major explanation of this, we will be seeing how we are reducing this metal oxide, that is your iron oxide to iron, by using your coke as a reducing agent in our next video. Just you have to keep in your mind that the reducing agent you have to choose in such a way that the curve for the metal oxide as an ore given to you, yes, it should lie at the top of the reducing agent which you are going to choose. That is the important funda over here.